Welcome to our session today. My name is Barry Bolding, and I'm the Director of High Performance, Autonomous, and Quantum Computing at AWS. Today, we are going to have a session where we'll be talking to you about the convergence of high-performance computing and machine learning to solve some of the most complex problems today. Today, I'll also be joined by Terry Cunningham, the CEO of Descartes Labs, and Jyothi Venkatesh, a solution architect in our high-performance computing team. During this presentation, we will talk about a number of things. I'll give a high-level overview of high-performance computing. I'll then talk about the application of high-performance computing to a computational fluid dynamics problem where we're using machine learning to greatly speed up and enhance the performance of the application. Jyothi will then talk about an ease-of-use example where we're using high-level AI services to drive a simulation. And finally, Terry will talk about the use of high-level machine learning and high-performance computing to solve complex geospatial problems with applications in such areas as deforestation. Today, high-performance computing is ubiquitous. It's everywhere. And whether you know it or not, you're surrounded by the solution of high-performance computing problems. Whether it's the coffee maker that you start every morning that's been designed by computational engineering and simulations in order to be efficient, or whether it's the car you drive using an assisted driving system, an ADAS system, where simulation has been used to test the safety of staying in lanes. Or whether it's the drugs that we use to fight diseases such as COVID, where they have done complex simulations to speed up drug discovery. High-performance computing and the simulations that go into that surround us in every aspect of our lives. Even when you pick up your phone and you look at the weather forecast for the day, behind that is a complex simulation that involves the dynamics of airflow and temperatures around the world. And simulations have gone into solving those problems so that it can make it easy for you to make that decision on whether to go outside or stay inside for the day. As we at AWS look at these complex high-performance computing problems, we face a challenge, which is how can we help to solve these problems in a way that fits the application to the infrastructure. In traditional on-premise systems, computer systems were bought and were used for many years, and often the application had to fit the underlying infrastructure. But today, in the cloud, we're able to provide a system in which you can fit the application to a number of optimized infrastructures. And what this does is it opens up a number of areas. It opens up the area of agility, where customers need to design their application to different types of infrastructure. And this is actually what happens when you combine traditional high-performance computing and machine learning. In this case, you often need a mix of general-purpose CPUs, accelerated GPUs, and high-performance networking, storage, and software. And that aspect of being able to fit the application to the infrastructure is key to what we try to provide at AWS. It's also important because it gives access to elasticity. And elasticity is critical to the tackling of problems that are project-based. Often when engineers are designing a new airplane or a new car, there's a spike in the workloads as they try to access new simulations and do very large simulations and models in order to meet deadlines for production and delivery. So as it's most important, we need to fit the application to the infrastructure that's optimized for the workload. The way AWS does this is that we work backwards from customer requirements, and that's key to the way that AWS works across all of our services. And the first types of challenges we look at with our customers are the operational challenges. And these are challenges around security, governance, and data transfer. And we sit down with customers and look at how the data needs to move, how the data needs to reside, what compliance issues are involved. We've created regions such as GovCloud where government customers can access application and simulation infrastructure in a secure way. We've created infrastructure for storage that allows for easy data migration in and out of the cloud and up and down through the stack of storage options on AWS, such as our FSx for Lustre and FSx ONTAP solutions. Next, we sit down with customers and we talk to them about their functional needs. And the functional needs in high-performance computing usually resolve around faster development cycles, the tools that help them derive insights, and easier access to data. A new requirement that's beginning to emerge from many customers is how can customers use machine and deep learning to derive increased business value from their high-performance computing simulation. And this is really what today's talk is about, and it's how that combination of machine learning and high-performance computing can be used to change the way, to reinvent and rethink the way that high-performance applications are being done. One thing that is true about the cloud today, AWS cloud, is that we can run any high-performance computing application. High-performance computing applications cover a wide range of areas. They can be computational fluid dynamics simulations of airflow around airplanes or automobiles that increase their energy efficiency. They can be looking at the subsurface of the Earth and trying to optimize and make sure that oil and gas reserves are maintained and that we're able to derive the maximum amount of efficiency out of those reserves. And again, as I said earlier, it can be in the area of weather forecasting. All of those are traditional computational areas for high-performance computing. And in every one of these areas, machine learning is being used to enhance the productivity of these applications. And that's what we're going to talk about today. Key to any infrastructure for high-performance computing, any truly supercomputing infrastructure, is that it has to have all the components it needs in order to not be slowed down or bottlenecked in any way. And it starts with compute. You need excellent compute, you need networking, you need storage. All of those have to be high performance for these applications. And on top of that, you layer orchestration and middleware software that allows for ease of deployment, automatic scaling of applications, such as you get with AWS Batch. And finally, visualization and analysis tools, such as AWS Deep Computing Visualization, that allows users to share data and share visualizations of data that they're deriving from their simulations. It takes all of these services to build up a system and that systemic view that allows you to optimize any piece of the high-performance computing workload. And now I'm going to step through a couple of the areas where these key services are critical and what AWS is doing to enhance these before I get into examples of the combination of machine learning and high-performance computing. First and foremost is the choice of high-performance compute technologies. And AWS has the broadest choice of core infrastructure for general purpose compute available today. This includes our partners such as Intel and AMD, with which we provide high performance application infrastructures for our compute instances in our EC2 infrastructure. In addition, we're innovating in the area of general purpose compute. And the AWS's Graviton processors, which are based on ARM technology, allow us to also provide general purpose compute with an ARM infrastructure and the best price performance. All of those are great as building blocks in that core compute technology. Many workflows, though, especially workflows such as machine learning training, require acceleration to achieve maximum result. And AWS, again, works with partners such as NVIDIA and Xilinx to provide high-performance accelerators that are tuned to machine learning training and inference applications. And in addition, AWS is developing technologies with our Inferentia and Trainium core technology accelerators. Those instance types also allow us to provide enhanced price performance and enhanced scalability for machine learning and inference workloads. All of these are ways that AWS is innovating in the core technologies that allow us to solve these complex hybrid problems at the cusp of machine learning and high-performance computing. That said, we're also pushing the boundary of new accelerator technologies, which will begin to show fruition over the coming decade. Quantum computing is one of those areas where we're looking at quantum computing accelerators that can enhance computational chemistry and physics, machine learning, and optimization problems. All of those are areas that are amenable to quantum computing, and AWS has invested in a quantum solutions laboratory at Caltech. We have a service, AWS Bracket, that allows customers to access a wide variety of partner hardware and simulation software in order to test out high-performance algorithms on quantum computing infrastructure. And that really shows the direction that AWS is going with enhancing these accelerator technologies for high-performance computing. As I said earlier, we take a systemic view to solving customer problems. And an example that we have built up within AWS that really exemplifies this system view is our EC2 ultra cluster architectures. And here I'm showing an ultra cluster architecture where we've built up in a single availability zone a very tightly coupled set of accelerator NVIDIA GPUs, a high-performance Lustre file system, and a high-performance network that is easily deployable by customers to solve very large training and very large HPC simulation algorithms. It's critical if you're going to combine the workflows of HPC simulation and machine learning that you have an infrastructure you can deploy quickly and scales with the size of the training models. And the EC2 Ultra Cluster is critical for this type of workload. And on the Ultra Clusters at AWS, we've solved some of the largest machine learning training simulations ever done. As important as all of these infrastructures are, it's really, as I said earlier, about fitting the application to the infrastructure. And different infrastructures are used for different types of high-performance computing applications. Whether those are tightly coupled workloads, such as computational fluid dynamics and weather simulations, or whether those are loosely coupled workloads, such as financial risk analysis, that can utilize and deploy compute resources around the globe to solve a single problem. At the core of all of these types of workloads, machine learning is becoming a critical component. And every one of these customers across these different workloads and their characteristics is beginning to ask this question of how can I get more value for my simulation? How can I solve my problem faster? And now I'm going to dive into exactly how combined HPC simulations and machine learnings work. An example of this is in the area of autonomous vehicles. And autonomous vehicle workflows are often broken down into two critical computational areas. The first is the training of the models that are used within the cars to make decisions, to do inference. And that's how the car can make a decision, whether it's seeing a person or a dog or a street sign, and make decisions about whether it stops, goes, turns. Those types of highly trained models take the infrastructures that I just showed, the infrastructure of the EC2 Ultra Cluster, in order to train those large complex models with the data that's coming off the fleet of autonomous vehicles every day. But that's not enough. What's needed additionally is you need to make sure the model you've trained is actually safe. And simulations of road driving are quite a different workflow. It's often done on general purpose CPUs, and it involves using simulation software very similar to gaming software that's used every day by gamers around the world. And that type of simulation software is how you test newly trained models before you redeploy them out into the cars. And this complex workflow can't break down. You need to have both aspects running efficiently and at scale. Other areas where we're beginning to see the combination of machine learning and HPC is in areas like cryo-electron microscopy, where this is a newly developed technology. The developers were awarded the Nobel Prize in 2017. And cryo-electron microscopy is really a new way of visualizing and imaging the molecular structure of molecules. And these complex devices that are now being used allow us to look into the heart of molecules and proteins and enzymes and see their structure in a very realistic fashion. But it also means that it opens up a whole area of simulation where we have to simulate what types of drugs can fit best into these molecular structures. And cryo-electron microscopy is greatly enhancing our ability to design drugs quickly and efficiently. In the demonstration later today, we're going to see that Jyothi Venkatesh is going to show. She's going to demonstrate a simulation of at the molecular scale that's very similar to the simulations that would come out of the images generated by cryo-electron microscopy. Customers such as Boom Aerospace every day are designing their workflows, which are usually around computational fluid dynamics, to design those airplane wings. They're looking at ultrasonic transports, how to have an aircraft that can break the sound barrier without causing sonic booms. That is the golden result that every aircraft manufacturer in the ultrasonic space wants to achieve, that supersonic aircraft. And that takes a lot of design testing and design of that aircraft, which wing design, body design, and which aircraft design is the most fuel efficient. All of those types of criteria are critical. And now I'm going to talk about an application that is directly applicable to such computational fluid dynamics models that Boom does. In the area of computational fluid dynamics, you're looking at complex flows, often turbulent flows, where air is flowing past an object very quickly. And those types of turbulent flows take very complex simulations that takes days and weeks on a typical conventional simulation in order to get to an accurate solution. And we sat down with some customers recently and we asked the question, can we get to the solution more quickly using machine learning? And what we did was we inserted machine learning into the heart of the simulation. And by doing so, what we hope to do is speed up that design process. Not to simulate as accurately as a full simulation, but can we use machine learning to train against accurate simulations and then do approximate simulations at a much higher rate? That would allow you to test out new designs for wings, new designs for car bumpers, new designs for airfoils in race cars, and be able to get to an answer much quicker. An example of this is for Formula One. And in the Formula One example, in race car driving, they often want to make sure that it's a competitive race. And they want to make sure that the airflow of the leading car doesn't obstruct the cars behind it from being able to pass. And that type of competitive racing lead airflow and how it affects the cars behind it is highly dependent on the design of the front cars and the way that the air is flowing around those front and leading cars. So as we look at how to combine HPC and machine learning, what we do is we do a very complex set of accurate input flow fields from accurate simulations. And we put those into a deep learning training model and train against that. And then create a situation where we can create the fluid flow around a car or a vehicle or an aircraft and in an approximate way. And we can do that training on the EC2 Ultra cluster that I showed earlier. Once you've done that, you really have a very interesting situation where I can now do millions of variants of that simulation without having to actually redo the original computational fluid dynamics. On the left, what I'm showing are 10,000 designs for a car that were all done in tens of seconds using the training algorithm and plotted against the friction and the airflow friction in order to get in order to get maximum fuel efficiency. And you can do tens of thousands of design explorations in a day. And then once you have a set of those that you think are likely, you can go and do the full computational fluid dynamics. And this is really offering up a game changer for how computational fluid dynamics can be done. And the speed up can be on the order of 1,000 or 10,000 times over doing the actual full simulation. So that's one example of the convergence of high-performance computing and machine learning. And now I'm going to hand it off to Jyoti, and she's going to talk about an ease-of-use application and driving a simulation through machine learning.
Thank you, Barry. Hello, everyone. I'm Jyoti Venkatesh, an HPC Specialist Solutions Architect at AWS. So during his presentation, Barry talked about the different key services that enable HPC on AWS. Now let's see how we can put together some of these key services, build an HPC architecture, run an HPC application, and take one step ahead and integrate AI ML services to see how that can simplify running your HPC applications. I'm going to start off by building the architecture here. So this is the base network infrastructure that you see here on the screen. So in the interest of time, I will not go into too much detail of how to build this base infrastructure, but just give you a brief idea of what this entails. So there is the AWS region, and you have a choice of different regions to pick from, and then an availability zone inside of this region, a VPC or virtual private cloud, which is your own virtual network inside AWS, where you can provision resources and run your workloads. Here I have chosen to organize my VPC into a public subnet and a private subnet. But you have the flexibility to configure these network settings as per your requirements. Now focusing on the key services for HPC, I'm going to start with compute. For compute, we have Amazon EC2, and you have a wide variety of instance types and sizes to choose from based on your application needs. So here in the public subnet, I have a head node, or this is an Amazon EC2 instance, which is also running a job scheduler like Slurm. Slurm is an example, but there are other job schedulers that are supported as well. And in the private subnet, I have a dynamically provisioned EC2. What this means is it is an elastic fleet of EC2 instances which can grow or shrink based on the request that is coming in via the job scheduler. Next, we have EFA, or Elastic Fabric Adapter, for inter-node communication. EFA supports OS bypass and in turn enhances inter-instance communication, which is critical to scaling tightly coupled HPC workloads. So these EC2 instances in this compute fleet are all EFA enabled. Next, we have the storage component, and you have different storage options to pick and choose from based on the I/O needs of your application. In this example, I have chosen to use Amazon FSx for Lustre, which is a high-performance parallel file system, which I'm using as Scratch. And behind this parallel file system, I have an S3 bucket, which is going to help hydrate this file system, and also as an archival tier for long-term storage. Next, we have the NICE TCV, which is a visualization component. It's a remote visualization protocol, which will help you to remotely connect to your head node from your local laptop and also perform visualization and post-processing of the results with a real-time experience. Finally, we have AWS Parallel Cluster, which will remove the heavy lifting of the configuration and building the cluster by automating the process. It helps build the cluster and also easy maintenance and management of this cluster. With the help of Parallel Cluster, you can also connect to this head node by SSH using a local terminal, or a NICE TCV session that I was talking about, which is the server component is running on the head node, and the users can connect to the session using an HTML5 browser or a native client from their local machines. We will see in a minute how that looks like. So this architecture here can be used to practically run different tightly coupled HPC applications. But for example, here we have chosen to run a molecular dynamics application like LAMMPS. LAMMPS stands for Large Scale Atomic or Molecular Massively Parallel Simulator. So for instance, the molecular structure discovered using cryo-electron microscopy that Barry talked about can be taken in as an input and modeled inside LAMMPS to study intermolecular interaction in other systems. So we wanted to run some scaling tests of LAMMPS on the architecture that we just saw. So we picked a LAMMPS use case, a 3D model with 27 billion atoms. And having the problem size constant, we added more instances as we scaled out. So more instances would also mean more cores. So the instances here I'm talking about are Amazon EC2 instances enabled with EFA. So on the chart here, you can see that the y-axis represents performance in time steps per second, and the x-axis represents the number of cores in the test case. The solid purple line is the actual performance that we measured, and the dotted green line is the ideal performance. So by comparing the two lines here, you can easily see that the performance, we were able to achieve a near perfect linear scaling with this particular use case of LAMMPS and this problem size of up to 50,000 cores. Now talking about how we are running HPC applications on this particular architecture that we just discussed. So, like I told you, we can use Parallel Cluster to connect to a DCV session that is running on this head node of the cluster, and the users can access this session using an HTML5 browser or a native client. And a session would look like what we see here on screen. And the users can open a terminal on this head node to edit their job scripts, to edit their input scripts, to run their jobs, and to monitor the jobs. They can also run post-processing or visualization. And we have a couple examples here on screen of how a LAMMPS visualization would look like. But what if we were to simplify this process further and eliminate the manual logging in, typing in the commands, and running the jobs, and instead if we were to use a voice assistant that would simplify this running these applications some more? So let's go ahead and take a look at the demo. There's a voice assistant running in the background which is receiving commands in English. These commands run remotely on the HPC cluster we discussed about and show you real-time output on the UI you see on screen. Alexa, list the nodes in my HPC cluster. So these are the details of the nodes in the HPC cluster. Alexa, show LAMMPS input file. This is the LAMMPS input file with 0.1 Kelvin as temperature with which we're going to run the first job. Alexa, submit a 4-node job with this in file. Now the job is submitted. Alexa, show jobs in the queue. So this job is running on 4 nodes as requested, and it's going to take a few seconds to complete. The job is completed. Alexa, show performance and CPU utilization of this run. So this is the performance and CPU utilization extracted from the logs. Alexa, change the temperature to 10 Kelvin in the in file. So with this command, we have changed the temperature to 10 Kelvin in the input file. Alexa, launch the 4-node job again with the new in file. With the change in the input file, a new job is submitted. Alexa, show jobs in the queue. Now this new job is running again on 4 nodes and it's going to be done in a few seconds. The job is complete. Alexa, show performance and CPU utilization of the latest run. Alexa, compare the dump files from these 2 runs. So this is the visualization of the results from the 2 runs. The window on the left is the result from the 10 Kelvin run where the molecular structure has changed significantly, and the window on the right is the result from the 0.1 Kelvin run where the molecular structure hasn't changed much. Thank you for watching the demo. And now here we are looking at the behind the scenes of what you saw in the demo. So the blue box here that you see on the top is the HPC cluster. This is the architecture that we just discussed a couple slides ago. And to this architecture, we have integrated AI ML services like Amazon Transcribe, which will convert voice commands into text, followed by Amazon Comprehend, which uses natural language processing, and it can extract key phrases for further processing. And these key phrases are processed inside of AWS Lambda, which is a serverless function. And here it will convert these key phrases into Linux commands that can be remotely run on the head node of this cluster via AWS Systems Manager. The output of these commands are then written into an S3 bucket, and the output is displayed on the UI that you were just seeing on this demo. So these services that you're seeing here on screen are all production ready today. So you don't have to wait to integrate them into your HPC architecture to make it simpler to run your HPC applications. You can get started right away. Thank you.
Hello, my name's Terry Cunningham. I'm the CEO of Descartes Labs. Thank you, Barry, for that awesome introduction. You mentioned how AWS is rethinking predictive workloads. Let's take a look at how we can reinvent business with predictive analytics. The biggest challenge we face, every company in every industry, is climate change. It's the existential threat of our generation. One all organizations will have to come to terms with. If we don't deal with it, it will deal with us. From our supply chain, our energy sources, asset risk, shareholders, stakeholders, and customers will all be fundamentally altered by these issues. Two of the reasons why climate challenge hasn't been solved are measurement and money. There hasn't been the computational ability to map the world at scale and time frame necessary to make change. Second, there hasn't been a willingness to sacrifice margins to make progress. It's an earnings per share, not ESG priority. But now is the perfect time because we finally have the technical and financial capability to change that priority. We need to flip the script. The winners will make sustainable supply chains their competitive advantage. To highlight this, let's look at net zero, where almost every CEO has made a bold round number commitment, but the reality is that not nearly enough is happening. We have yet to bend the curve. It just keeps getting hotter. Again, the disconnect between actual progress and vague commitments comes from a technical and financial challenge. Companies have simply lacked the ability and a compelling reason to invest in these hard problems. But the tide is changing. Consumers and stakeholders are demanding action and accountability. Enterprises must find a balance between maintaining profitability and meeting stakeholder expectations. With the incredible advancement you just saw from AWS, it's now possible for us to make predictions using geospatial data, machine learning, and HPC about the outcomes that matter the most. Let me show you. There's a rule in business that you have to measure what matters. In sustainability, we say for good, measure. If you can't set quantitative goals for your company, you can't create a new and better future. We have to start from first principles. 25% of greenhouse gas emissions comes from land use, and we need tools to measure them. We look at all parts of a supply chain and use geospatial data like satellite image images, LiDAR, weather, mobility data, and so on, to build quantitative models. Here's an example that predicts and quantifies tropical deforestation. Our system watches for patterns that anticipate deforestation and then detect and measure it when it occurs. Weight it by the amount of carbon affected. Remember, not every hectare of forest is the same. This allows agribusiness to certify their supply chains as sustainable and local governments to attack the problem before the forests are destroyed. But with no carbon tax or a working offset market, global enterprises need a different incentive to fund an effort like this without impact to their bottom line. Companies are responsible to diverse groups of shareholders who expect profitability along with doing the right thing. However, here's the magic. Using the same geospatial data we employed to predict deforestation from space, we can quantify supply chains for a different reason, to forecast commodity prices, for profit forecast. The fundamental changes in production, inventory, and demand that are needed to assess the sustainability profile of a company's actions are also the same factors needed to forecast commodity prices like palm oil, steel, shipping, etc. Using massive amounts of compute and constantly updating remote sensing data, we forecast the impact that observable changes on the ground will have on prices, optimizing the purchase patterns, driving savings in the tens of millions of dollars per year. And amazingly, the same data that anticipates and mitigates these price fluctuations will fund, protect, and enhance your environmental reputation. It's a free option, a dual use of the same insight. Two critical activities that companies have that are transformed using geospatial data, machine learning, and HPC. This is precisely what we did for a major agribusiness client recently. Tens of millions of dollars of savings and better commodity production and price forecasting helps fund the cost of certifying the sustainability of the supply chain. Using that concept, we came up with a novel way to answer what is going to happen by capturing and analyzing all the sensor data all the time. That way, we can look for patterns as they emerge and predict outcomes that our customers most care about, from prices to sustainability. So when Cargill wants to more accurately predict the price of corn, they come to us. When Rio Tinto wants better targeting for mineral exploration sites, they come to us. In the national security domain, where the US government wants to know where China plans to build its next missile site, they come to us. We have done this for hundreds of use cases. The proliferation is evidence that all companies will eventually incorporate geospatial analytics into their operations. To do this, you need a cloud supercomputer and all of the world's sensor data. Planetary scale analysis requires planetary scale compute. AWS Descartes Labs are unique in their ability to do this. To give you a glimpse of how we do it, we built one of the most powerful AWS supercomputers in the world that allows us to digest hundreds of terabytes of sensor data in real time to build constantly updated models of the Earth. We then use AI to search this model for patterns and turn it into predictive analysis for our customers. The cloud allows us to redefine what it means to be a supercomputer. These are just some of the AWS services that make that happen. EKS, or engineers, can leave managing the K8 environment to AWS and solve geospatial problems. Lambda to revolutionize our ingest pipelines, Redshift for smart storage, StorageLens to understand for use and performance of the cloud environment, and Batch to enable our scientists and their unique computing needs. So now imagine what this could be in the future, a living, breathing map of the world's activity that quantifies emissions by mapping supply chains at planetary scale. This can be applied across all industries. Having a self-interest and a social interest are no longer mutually exclusive. All enterprises will need to be geospatially informed if they stand a chance at surviving the changing landscape. Geospatial data needs to be integrated into everyday functions of major companies if we have a shot at saving the planet. A few thought leaders are doing it now. It's so simple for them because every day they do is already running through AWS. The tech is available, the funding is available. It's the perfect opportunity. Let's take action and let's do this now. Thanks, and back to you, Barry.
Thanks, Terry. That was fantastic. It's always exciting when we see how customers are putting AWS to work to solve their most complex problems. Hopefully today we've shown you some examples that have inspired you to rethink the way that you're approaching high-performance computing problems and how you're deriving value from the solutions that you get. We believe that by rethinking these problems and then beginning to reinvent the workflows that you have, you can get to results that change and dramatically increase the business value that you're seeing. The agility, the economy of scale, and the elasticity of AWS, combined with these complex workflows that bring together machine learning and HPC, are going to be how we solve problems such as climate change and these complex problems today that around engineering and design. I want to thank you very much for your time today. Enjoy reInvent, and you'll see lots of great demonstrations and have a lot of things to think about as you go back to your jobs.